NP separately, right? Because they can convert into each other. So that assumption is valid under chemical equilibrium, right? Once this rate of conversion falls below the Hubble expansion rate, right, then chemical equilibrium is lost.
Then we will have to see other chemical, like we have to separate P and N.
Yeah, I mean, but in that process, right, neither of these is valid, right? Because P and N can get converted to each other, but the rate is not sufficiently high so that you have chemical equilibrium, right? So in that case, we have to do more work, right? And that's what we will discuss today. But eventually, right, as you said, that once this conversion stops altogether, then we can think of P and N as separate concept quantities.
This chemical equilibrium that we discussed is until 1 MeV.
Yes, until 1 MeV, exactly. That's right. Okay, below 1 MeV, that chemical equilibrium is lost,
because
right?
The first equation, reaction, which is governed by the interactions, is not
exactly
dominant.
Exactly. So anything that changes protons to neutrons and vice versa is weak interaction. Like strong and electromagnetic interaction doesn't change protons to neutrons and vice versa, right? So because of this, at 1 MeV, it goes out of equilibrium.
I thought that because, let's say, I thought that the neutron decay process, I mean, the equilibrium shifts the other way. I thought that it came from the reaction rate thing because, I mean, this reaction, the neutron decay process, let's say, so it depends on the density of the neutrons, but on the other hand, the reverse process, it would depend on the density of protons, electrons, as well as neutrinos, right?
Exactly, yeah.
So, and then with the expansion of the universe, the densities would fall 1 by lambda cube.
Yes.
So, I mean, the reverse process would become the rate would fall down very, I mean, order of magnitude difference.
Yeah, but that, I mean, as long as that was larger than the Hubble expansion rate, right, it would still reach chemical equilibrium.
The reverse process, if it had been, the rate of that process had been larger than the
Yeah, imagine that the universe was not expanding.
Okay.
Right?
Yeah.
It's just a gas of neutrons and protons, even at very, very low temperature. Right? Their chemical equilibrium will be established. Yes. Right? Even though the neutrons are decaying, and that will be part of the process. What you will find is that when you actually use a chemical equilibrium formula to calculate the ratio of Mn to Mp, it will Nn to Np, it will turn out to be very small. Okay? But that takes into account all these processes. Okay? So the Hubble expansion rate is important, right? If there is no Hubble expansion, then you will always establish chemical equilibrium if you wait sufficiently long.
Yeah, you mean to say that Hubble expansion rate is some sort of scale with which we compare the rates?
Exactly. Right? So both the forward rate and the reverse rate should be faster than the Hubble expansion rate in order for chemical equilibrium formula to be valid.
But it seems that the reverse rate, let's say, is very much smaller than the forward.
Doesn't matter. As long as any rate is smaller than the Hubble expansion rate, you have to forget about chemical equilibrium and do things other way. Right? But as I said, if the Hubble expansion was 0, right, then it is true that reverse rate may be smaller than the forward rate. But chemical equilibrium formula, you know about that. Okay. When you actually calculate the number of protons to number of neutrons, you will find the number of neutrons is very, very small.
Electron positron energy density will be calculated constantly using the thermal equilibrium formula.
Yes.
So that will valid like throughout.
That will be valid till very late. Yeah.
Even after CMB.
Yeah. Eventually, right? For example, after last scattering, it cannot be valid, right? Because there are no photons. Photons don't scatter. Okay? But before that, electrons will bind to protons. Right? So this electron positron, you cannot think of the electron positron separately anyway.
And the other thing is about the baryon asymmetry. We are using this baryon asymmetry always to set a value about whether mu is 0 or mu is approximately equal to the mass.
Yes.
So is the problem of baryon asymmetry is about finding a right chemical potential irrespective of the baryon asymmetry?
Yeah, that we know what the baryon asymmetry is, Nb over N gamma, right? and you have to adjust the chemical potential so that you get that value.
So to solve the problem of baryon asymmetry, is it like someone need to find how the chemical potential will vary with respect to temperature for these species?
No, within standard model, you cannot solve the problem of baryon asymmetry because you need a baryon number conserving process. See, here you are taking the baryon asymmetry as given to us because we know today that there is a baryon asymmetry, and we are just studying consequences of that. Right? We are not trying to explain baryon asymmetry.
If there is a baryon asymmetry, then the chemical potential should behave like this.
Exactly. That baryon asymmetry tells us what was NB over N gamma, right? And based on that, you can calculate what the chemical potential should be.
This cannot be explained by the standard model because the baryon number conservation is not.
Well, the point is that what cannot be explained from the standard model is why there is a baryon asymmetry. Right? Normally, if we assume that the universe started without baryon asymmetry, then standard model cannot explain why the baryon asymmetry is created.
Somewhat sees like if you know appropriately how to explain the chemical potential variation, then this will automatically.
No. The point is we are using the fact that NB over N gamma is non-zero, right? As long as you assume that, rest follows. But why is NB over N gamma non-zero? That you are not explaining, right? Given NB over N gamma, you can calculate how chemical potential varies. Okay? But NB over N gamma is not something that we are using as being given to us. Okay? If it was zero, then the chemical potential should behave differently.
And the one thing about the radiation dominated error approximation that we are making,
Yes.
So like that can be a possible rapid expansion in the early universe.
Yes.
So after that, some phase transition will happen, and it will again go to some radiation dominated era.
Exactly. So you have to return to radiation dominated era, because we know that if we just extrapolate backwards, right, based on standard physics, we know that the universe must have been radiation dominated earlier. Yes, just evolve what we know today backwards and see what it should have been at that time.
Are we saying that the initial the period, the epoch before radiation domination was small because of some experiments which gave us the age of the universe?
No. The age of any experiment that gives us the age of the universe is after the time that we are discussing, right? Because what can you use to measure the age of the universe, right? The ages of known objects shouldn't be larger than the age of the universe. And known objects like stars were not present at that time, right?
Yeah, smaller. Those which we observe have smaller age than age.
Exactly. Right? That's the only way you can put some limit on what the age of the universe is experimentally, right? And those limits certainly are not going to be affecting what happened before this time, right? Universe might have spent billions of years, right, in early phases.
This is an assumption that the time period before radiation domination is small.
No, we are not assuming anything, right? We are just counting age from, say, the time when the temperature was 10 MeV.
That is true, but when we say that the initial state of universe, the universe spent very less time in the initial state compared to what it's.
As long as the universe was radiation dominated, that you can check that it spent less time in the initial phase, because you can just continue this equation backwards, right? Because if there is any other phase, we don't know if that is true or not. And there is that period, right? The age that we had at that period will have no bearing on what we see today, right? So as far as the age of the universe is concerned, we can define it to be the time from when the universe was 10 MeV till now. Yeah, that is the practical definition of the age of the universe, which will not affect, which is good enough for anything that you can do with the age of the universe.
Discussing the state of the universe before 10.
Before 10 MeV, yes.
Discussing it is like, can we discuss it?
Yeah, we can discuss it, right? Except that within the standard model, right, there's not much to discuss, because once thermal equilibrium is established, anything that happened before got wiped out, right? We could have asked if that period could produce baryon asymmetry or produce dark matter. Right? Within the standard model, you cannot do it. Right? So we'll discuss it, but we have to go beyond the standard model, right, to get anything useful out of that period. Any other question? Okay, so let me remind you that we are trying to calculate xn as a function of time, and xn was defined as the number of neutrons divided by number density of neutrons plus number density of protons. So the fraction of the baryon which exists as neutron as a function of time. Okay. And the process is changing n to p and vice versa. Okay, these are all weak interaction processes, so let me write them down. So n okay, so these processes are the ones that are responsible for changing n to p and vice versa. The first one, and there is something, and thank you, yeah, thank you. So the way we'll go about it is we have to calculate the reaction rates for each of these. Okay, because we can estimate that this will fall out of equilibrium below 1 MeV, right? That is the same calculation that we did for the neutron decoupling because it's a weak interaction process. But if you want more accurate result for how xn changes with time, we need to know the actual reaction rate. Okay, so this you can calculate from quantum field theory, but I'll write down the result for one of the reaction rates. So we'll calculate, consider n plus e plus going to p plus mu bar. Okay. And so the result for this we had already seen earlier. So rate per neutron that we are looking at from the point of view of the neutron, right? That if we focus on a particular neutron, okay, what is the probability that it is going to make transition into proton via this process, right? So that's the meaning of rate per neutron. Okay. And this is given by sigma times V plus Ne plus. Okay, sigma is the cross section. V plus, remember there is a relative velocity between the neutron and proton, neutron and positron that will be coming in. And because the neutrons are non-relativistic, right, we can just assume they are at rest. So the relevant velocity is just the speed of the E plus. Okay, that's why V plus. And then this is the density of positrons because it has to collide with this. Okay, so this is the general formula for the rate. Okay. So now I'm going to write down the formula for sigma. Okay, and you will see many of the structures that we had earlier, but it will also be more accurate than the level at which you worked earlier. Okay. A is a constant. So G weak is roughly what you saw GW square over MW square, right? You remember weak interaction process had this. Okay, and its value, which is more important, is 1.166 times 10 to the minus 5 GeV to the minus 2. Okay, it's GeV to the minus 2 because there is a 1 over mass square in this formula. Theta C. This is the Cabot angle. So I'll write down the results for all of these. So GA, okay, is the axial vector coupling. Okay, this also is just a number. So this is 1.257. And cos theta C is the Cabot angle is close to 1.975. Okay. The details are not important, but the important point is that you have an explicit formula that you can use, right? And this you get from quantum field theory, that the particular result for the cross section. The other thing I should say is that typically the cross section, it's n plus e plus, right? So the cross section will depend on the spins, okay? And this one that you have, okay, is averaged over spins, okay? But on top of that it has been multiplied by 2, okay, for reasons that I'll explain, because it doesn't count it basically counts both positive and negative helicity E plus, right? E plus has 2 spin states, it just adds them together, okay? So if you think of this sigma as an average, right, the actual average cross section is half of this, okay, that is averaged over the spins, okay. It has been multiplied by 2 just to account for the fact that E plus has 2 polarization states, okay? And we will see where that comes in the formula that I am going to write.
You said something in the beginning about why velocity of the positron dictating the rate.
Yeah, because neutrons are non-relativistic, right? At 1 MeV, they are non-relativistic, so their speed is almost 0.
It's like assuming that every collision will result into this reaction.
No. It is telling us not every collision will take into this reaction. Most collisions may not produce anything, right? Or they may produce something else, forward scattering. Okay? The sigma is a cross section that tells us that this is the number that you get when this is the sigma that we'll use if we want the final set to be p plus nu v bar, right? The actual collision may produce other things, that's not counted inside sigma. Okay? So we are not assuming that every collision will produce this, but this sigma counts only those collisions that produce this, right? That's the way you normally define cross section for different processes. This is the tree level result, but also, I mean, there's neutron. So you have to do some trick to apply quantum field theory, because neutron is a bound set of quarks, right? So that's why this GA comes in, right? But roughly you can think of this as a tree level result in an effective field theory, okay, of coupling of the weak interaction physics to the baryons.
And that coupling is effectively given by GA.
Yeah, normally, right, the GA would have been 1. Okay, this for electron, for example, right? I mean, the fundamental particles, right? It's the V plus A or V minus A coupling, right? The vector coupling and axial vector couplings are equal, but because it's inside the neutron, right, things change. Okay, so this is experimentally measured, this GA.
What is E nu is entering into the cross section?
E nu is the energy of the final state neutrino. It will depend on the energy of E plus, right? Because total energy is conserved and we are going to use that. So E nu, yeah, I should have said E nu is the energy of the neutrino of nu bar. So now we have to convert this into some rate. So let's denote by Ne plus the number of E plus between P and P plus dP. Okay, this is in the thermal gas. Okay, because the E pluses are being picked from the thermal gas that is present, right? So let's suppose that this is well, Ne plus. I should also include dP. Then this Ne plus dP is given by 1 over 2 pi square, and then P square dP times 1 over e to the power earlier you are calculating the total number of positrons or of particles, so you integrated over everything. Okay. We also had a factor of 2 earlier because the positron can exist in 2 spin states. Okay. That factor of 2 we are not including here because that is already included in this definition of sigma. Okay, otherwise you have to put a half here if we think of sigma as the average cross section and put a factor of 2 there. Okay, but it's
any spatial number density of positron, right?
yes, indeed. We are always talking about the spatial number density.
So if you multiply with dP,
P is so deep. Okay, this combination, right? I mean, there is a P square dP which has gone in here. This is the d cube P, right? We have already done the angular integral, right? That's why I have written it as dP. Otherwise, I would have written Ne plus d cube P, and in this case, I'll have a d cube P, right? And then you have to do the angular integral separately. Okay, but
suppose we have phase space.
yes.
Phase space number density. Suppose F is the phase space number density.
Yes.
If we integrate it over spatial directions d3x,
Yes.
then we get a number of particles in the interval PE plus dPE.
Yes. If we do angular integral.
Spatial integrals. D3 P vector.
Spatial integral means the actual position of the particle.
Yeah. So
Position of the particle is not important here, right? Because that V over 8 pi cube. See, this 1 over 8 pi cube, see the 1 over 2 pi square, if you remember where it came, there's a 1 over 8 pi cube times 4 pi, right? This 4 pi p square dp.
that is fine.
Okay. And there's a V here. Wait, there's a, in the full number density, there's a number, there's a V. We convert it to density by dividing by the volume. Right?
That V is 1.
That V is not 1. That V has gone because you have divided by V. This is an expression for the total number.
Fine. I am saying you have phase space.
Yes.
You have phase space density.
Yes.
If you integrate over d3x,
Yes.
you get number density in the momentum space.
Yes.
Between p vector plus
Yes.
p vector to p vector plus dp vector.
Yes.
So this NP plus is the number density in spatial number density. How are we saying that it is the number in P?
No. If you integrate over P, it will be the spatial number density. Earlier you are integrating over P, right? That was the number of electrons, the number of positrons per unit volume, irrespective of what the momentum are. Right? Now we need the information about the momentum because the cross section depends on the momentum. Right? So you are now asking what is the number density in the interval between P and P plus dP. Right? If you integrated our momentum, we would have gotten the previous formula, right? Where we calculate the total number density. Right?
If we remove the integral sign, then whatever is left, that is the number density you are talking about.
In the momentum interval, exactly. That is the number density you are talking about, yes.
I thought the entire equation was per unit volume. The left hand side, the rate per neutron, it was per unit volume, right?
Not per unit volume, per neutron, one steps are per neutron. Neutron is moving, right? If you remember the way you got this formula, we looked at the cylinder, right? And we multiplied by the number density. right, to find the number of collisions. Right, there is a cross section sigma, and you multiply by number density to find the number of collisions. Now you are saying that it's not enough to just consider the number density. You have to know a number density for a given momentum range, because the sigma depends on the momentum.
I was thinking about this rate, sigma v plus ne plus. I mean, that's
Yes.
rate per neutron per unit volume, is it?
Ne plus is per unit volume, certainly. No, not rate per neutron. Neutron is moving, right? Or neutron is stationary. There is a unit volume there. There is one single neutron.
Okay, but the right hand side electron density is
Per unit volume, exactly. Because we had the cylinder, you have to multiply by the unit volume, right? By the density. That is per unit volume. Right? So the electron density is per unit volume. Right? But now we have to also keep track of the momentum that the electron carries, because sigma is not the same for arbitrary momentum.
Sigma is a function of momentum, so that therefore we integrate over all momentum.
There we integrate over all momentum, right? Instead of just multiplying sigma by ne plus, there is this formula, right? You should really think of this as the momentum integral of sigma times ne plus.
And what is the left hand side? The rate at which
A single neutron is getting converted to proton by this process. If you wait for time t, right, the probability that it will get converted to proton is t multiplied by this rate.
okay. This is the rate per single neutron.
Yeah, for single neutron. Right, because this picture is for a single neutron, right? Any electron that is inside this cylinder, right, is going to hit the neutron and convert it to proton. Not that every time an electron hits the neutron, it converts to proton, right? That is not true. But sigma y is defined in such a way that as if it's within this cross section, then for counting purpose, you can think of every time the positron hits the neutron, it converts to proton.
That Ne plus and this Ne plus are different, right? Because that
Yes, so you have to do the integral. So let me write down the formula, then it will be clear. So the rate per neutron is given by integral dp p square 1 over 2 pi square 1 over e to the power e plus over t plus 1 times 2 pi square a e nu square. Let me just check if I've got everything. Yeah. Okay, this is Ne as a function of p plus, right? And then we are integrating over p. Right? If this was independent of p, say E nu depends on p, right? If this is independent of p, we could have just taken this integral out and multiplied by that Ne plus. Right? But because the cross section depends on the electron energy, right, via the final state neutron energy, that we have to do the integral. We cannot just multiply by the density.
So that rate per neutron, that is formula that we have written,
Yes.
that's really the rate for a neutron which is traveling with momentum p.
Yes. So I could have written it as integral dp Ne p plus p is d, right?
That's a total
That is total rate,
rate, which is this. Basically.
which is this one. Right? Earlier we are using this crude formula because we just wanted an estimate, right, for the neutrino decoupling. Right? We just wanted to know at what temperature neutrinos decouple, right? Because the final result really didn't depend sensitively on the precise value of the temperature. Okay? Whereas here you want to be more accurate, right? And for this we have to do this integral, right? So this is the formula. Well, this is not yet the full formula. I have to add multiply it by something else. But based on what I have told you, this should have been the formula. Is this point clear?
And velocity of positron doesn't come into.
It doesn't come because the sigma is written as 1 over V plus, right? And here there is V plus multiplying it, right? So they just cancel.
That it doesn't feature at all. I mean, the energy is there.
It comes in, yeah, exactly. It comes in, but this factor of E plus gets cancelled.
That any plus dp.
Yes.
That's a more precise thing would be to say that that is spatial number density of a polytron between p.
Yes, indeed, that's the thing. Yeah, it is spatial number density of positrons that carry energy between p and p plus dp. Right? Earlier, we are talking about Ne plus, which is the total integrated portion, right? And that in this language will correspond to basically take this integral and pull the other factors outside. Right? This 2 pi square a e nu square etc. If you pull outside, right, that's what you will get. That's when you will get back the earlier formula. Right? That's what we did earlier, right? You remember that for E nu, we saw that there should be an E square by dimensional analysis, and we just substituted this by T square. Right? That's how we estimated the formula for neutrino cross section. Is this okay so far? Okay, but there is one thing which is missing, and that is the following. This sigma that I have given is just the scattering cross section that you calculate from quantum field theory, that is in a vacuum. Here you are working in an environment, right, where there are already some particles present. Okay. So you have to make sure that the final state neutrino, right, is unoccupied, because neutrinos are fermions. Right? If the final state neutrino is occupied, then this process cannot happen. You cannot produce a neutrino in the same state where already there is a neutrino, right? So you have to multiply by a probability that the final state neutrino is unoccupied, and that is again given by this thermal factor. So it's 1 minus the probability of occupation of the final state neutrino is e to the power e nu over t minus 1 plus 1.
Must have wanted to already in the cross section.
No, in the cross section calculation, you do the calculation in a vacuum. Quantum field theory just assumes that the final state is vacuum, right? You are producing things in a vacuum where there are no neutrinos to begin with, right? Here the final state has a neutrino, and that can suppress the possible production. So this is just the Boltzmann factor for fermions, right? So this quantity is basically 1 over 1 plus e to the minus e nu by t. Is this clear?
Then how does mu come into this cross-section formula?
How does E nu come in this? Oh, E nu comes just from Feynman diagram calculation. Right? That the vortices have done some dependence on the energy of the neutrino. Right? But that calculation doesn't assume that the final state is empty. You are just producing this in the vacuum.
How we identified this is the factor?
These are the standard Fermi statistics, right? The 1 over 1 plus 1. Yeah, this is the, I mean, this factor is the occupation number, right? E to the minus e nu over t over 1 plus e to the minus e nu over t, right? That is the occupation factor. That is the same as this. And you want it to be unoccupied, so you have to subtract this from 1.
If there was some bosonic particle instead of neutrino, you are saying it would have been what?
It will be enhanced. It will be enhanced.
Enhanced.
The probability, right? Because if the final state is already occupied for bosons, right, the actual probability of producing a state in that becomes larger than 1. It enhances the probability for producing that.
Is there any reason for this?
For what?
Enhances. Why does it enhance? Like Pauli exclusion principle tells us that.
Yeah, maybe physically it's hard to explain because exclusion principle is easy to understand, right? But for bosons, why it's enhanced, right? I mean, this is something you see in stimulated emission and so on, right? That if there is already a particle, it enhances the probability of decay, right? So it's the same physics that causes stimulated emission, right?
Can you understand it in terms of like anti-symmetric states and symmetric states? So,
This is statistical.
Yeah, you can. Okay, I mean it is statistical, but it comes from the symmetry, right? The fact that it's basically, if you think in second quantized language, right? A dagger to the n, right? It's easier to now put another A dagger. Okay, if you look at the probability, right? Because for the bosons, right, the creation operators can be applied as many times as you want. Right? If there are already n particles, right, you can see that the next one will be higher probable. If you try to now put another photon, right, the possibility will get enhanced.
we can like
The probability of production, right? I mean, if you just do it in terms of Feynman diagrams, right, you can see from that language that if the final state has more particles, right, the probability of producing another particle in the final state will be larger, right? Because here what you are saying is that the final state is not the vacuum, but you are producing the state in a environment where already some states are filled. Right? You can set up this Feynman diagram calculation for this, and from that also you can see that for the bosons it gets enhanced. But as I said, it's not Pauli exclusion principle is easy to understand, right? For bosons, why the enhancement works. I mean, you can see that it is there, but it's intuitively it's hard to see how it happens.
If we, instead of doing the calculation in vacuum and then taking into account the Boltzmann separation for pharma, if we would have done the same calculation about Harman state of the cube,
Yeah, then this factor will automatically come.
it will be the same.
Exactly. Yeah.
Last time also we calculated some cross section, then we by dimensional analysis we put some T or something.
Yes. That is this E nu square factor. I mean, here I have given the precise form, right? That E nu square, what I have put here, right, was replaced by T square last time. That's for dimensional analysis. Is it okay? Any other question? Okay, so you are now going to manipulate this. So first use energy conservation. We have Mn plus E plus equal to Mp plus E nu bar. Well, what I have called E nu is actually the E nu bar. Okay, let me write it E nu since I have said it E nu, but this is the energy of antineutrino. So this one is square root of P square plus M square. Okay. So this we can write then E nu as Mn minus Mp plus square root of P square plus M square, which is Q plus square root of P square plus M square. So remember that yesterday we introduced this definition Q, which is Mn minus Mp. Okay. So E nu is not an independent variable, right? I can write E nu in terms of P. Okay. But we'll write slightly differently. We'll use E nu as the independent variable and rewrite P in terms of E nu. Right? Just, that's just a choice. Right? It really doesn't make that much difference. Well, one reason is that the e's appear in the exponent, right? So it will be easier to write in terms of e rather than p. Okay, other there will be square roots in the exponents, right? But we are just going to make a change of variable. So we get p square plus m square. So p square plus m square as q plus q whole square. Okay, I should have said also something else. We define the variable q as minus e nu definition. Okay, and in fact we'll use the variable q to do express the final integral. Okay, so q will be negative, right? Q is minus e nu. So p square plus m square will be q plus q whole square. You can see from here, right? We get minus q from this as q plus square root of p square plus m square. Okay, so if you bring q on this side, p square plus m square is q plus q whole square. Okay. And this tells us that PE dP is q plus q dq. Okay, just by taking the differential on both sides, because we are trying to write everything in terms of q, right? So p we want to eliminate in terms of q. And furthermore, p from this is q plus q times 1 minus m square over q plus q whole square to the power half. Okay, I just took m square on the other side and took the square root. Range of q, let's find that. Okay, so we have q as minus q minus square root of p squared plus m squared. So you see that q has to be less than minus q minus m. So using all that, we are going to now rewrite this formula. So rate per neutron. So for this process, n plus e plus going to p plus mu e minus, no, n plus, I calculated n plus e plus p plus mu e bar. This is already calculated. Rate per neutron is given by, so 2 pi squares cancel. Okay, a is just a constant. So a times integral 0 to, well, integral minus infinity to minus q minus me dq. So PE dP we wrote down q plus q dq, q plus q. Then we have another factor of p, right? Because this is d times p, p times p square. So the other factor of q, p gives you this q plus q 1 minus m square A is just a constant, so A comes out. That has come out already. And then E nu square is Q square times 1 over 1 plus, now E plus is this one. So that's minus Q minus capital Q, right? And this is 1 over e to the minus E nu by t. So that's 1 plus, pardon?
Yeah, I think Q plus Q should be within a.
What should be? Yeah, Q plus Q is inside the bracket. Yeah. Yeah, minus is outside. Minus of Q plus Q over. Yeah, and then a P square. See, P square has gone because of this P square. We wrote dP times P using this formula. Right? And another factor of P I put in explicitly. Okay, so let's just clean up this formula a little bit. So this is A times integral minus infinity to minus Q minus ME dq. Then we have Q square, Q plus Q square, 1 minus ME square over Q plus Q whole square to the power half times 1 over 1 plus e to the minus Q plus Q over T, 1 over 1 plus e to the Q by T. Oh, I should have said something which I didn't. This T is T nu, right? Because this is the probability for the final state, neutrino being unoccupied. So that's follows the thermal distribution, but with the neutron temperature, T nu, which is not the same as T. So I should put that here. This is T nu.
If it says some greater than one mega electron volt, so even in thermal equilibrium.
Well, if it is, then T nu is T, right? We are just doing this not at. I mean, this is supposed to be valid even below MeV, right?
These kinds of reactions.
Yeah, the reactions are there. I mean, they may be small, right? But this particular reaction produces this rate. Right? Then you have to decide whether it's small or even if it's small, maybe around 1 MeV it's not so small. Only way below 1 MeV it will become small. Right? If you are trying to get an accurate result for Xn, right, you have to take this into account.
I mean, anyway, for greater than MEV, we can just put in the new equivalent.
Yeah, exactly. Because T nu T relation you have calculated separately, right? So that you have to put in this evolution equation. Okay. Any other question?
We are assuming P plus positrons to be relativistic here, right?
Not necessarily. You have put the Me, right? So you have to assume that they are not necessarily non-relativistic. You have used square root of P square plus M square, right? So as the temperature comes down, they go from relativistic to being non-relativistic, but that is accounted for, right? Because you have not used, for example, that E is P.
Formula is general, right?
This formula is general. Square root of P square plus M square is general formula, right?
But for E nu, we have.
Yeah, neutrinos you are assuming is relativistic. Because neutrinos are massless at that level, right? Neutrino masses are much lower than that MeV scale. So as far as the neutrinos are concerned, we are assuming them to be massless.
And you can use this here, mass the
Neutrino mass?
yeah.
Oh, the fact that well, maybe we haven't used it anywhere yet, right? Because everywhere we had E nu only. Yeah, so you have not used it, right? But we are implicitly assuming that it's massless.
This formula can be used to calculate the rate at any time, and then we'll check if it is greater than.
No, we'll not check anything. We'll just use this formula to calculate dx and dt directly, right? And then whether it's greater than or less than will not matter. Because as long as you are calculating, finding the evolution rate, right, it will give what it gives, right? It should happen that when the thing is in thermal equilibrium, that it should agree with whatever that predicts. Yeah, you can. Yeah, because that checking will be the same calculation that we did for the neutrino, right? Because if you look at the various factors, right, there is these integrals and all, right? But for an order of magnitude estimate, we can just use the same formula. Right? All you did there was that you replace by nu square by t square, right? And which is still roughly true here when you look at these integrals.
What about the backward relation?
Yeah, so this is only one of 6 processes, right? So you have to do the other 5 and then put them together.
Here we will take into account this expansion or anything. So if this rate comes out to be less than expansion will not happen.
No, it's not that it will not happen. It will be insignificant, right?
That will have to account differently. Or
No, you don't have to do it differently, right? If this reaction rate happens to be small, right, it will just not contribute to the evolution, right? See, at this stage, you have not assumed anything about whether the expansion is fast or slow, right? We are just doing the calculation instantaneous rate calculation, right? And the Hubble expansion will come in eventually, right? But for this process, we don't need it.
can we include expansion in the temperature term?
Yeah, the Hubble expansion will come how the temperatures fall as a function of T. Right? T nu and T falls is a function of time. There the Hubble expansion rate goes in.
So, I mean, basically, if we plug in the Hubble expansion rate, I mean, that dependence into the temperature, let's say after we compute all these dates, somehow, if it turned out that these things fall, become very insignificant as a time.
It's okay, right? What is wrong with that, right? They're just, we are substituting in the equation. If some terms in the equation are small, the computer will take care of it, right? If we just use it to evolve it in a computer, right? Doesn't matter if sometimes terms are small. Okay, so fortunately, it turns out that you don't have to do 5 more calculations, right? This is all that you need. Okay. So I'll now write down the total rate. Okay, so rate. So R, let me write R n to p of t. This is the total rate per neutron. Rate of n to p per neutron, which basically means that you are calculating the same thing except that you have to also add these other processes. N going to p plus e minus plus nu e bar and n plus nu e going to p plus e minus, right?
Sigmas won't change in these calculations.
Sigmas will change, but they will change in a way so that the final result is nice. Okay.
The temperature will be different now, no? Because the finals, this was neutrino temperature.
Yes.
Now we have E minus, the final state.
Yes.
E minus in one of the processes.
Yes, indeed.
Will it be E minus?
Yes, of course. When you calculate the probability of it being unoccupied,
That factor we have.
that factor will have the E. Because now E has to be unoccupied, right?
Right.
But the thing on the, plus Q thing will have a E.
Yeah, let me write the formula, then you will see where these things are. is the same formula except that the range of Q includes minus infinity less than or equal to Q less than Q less than or equal to minus Q minus M. This was already there. Right? This came from the N plus E plus going to P plus nu E bar. Then it includes, let me be accurate here, minus Q minus ME less than or equal to Q less than or equal to minus Q plus ME. Sorry, this is not, this is a one missing branch, 1 minute, sorry. Just in, yeah, this same integral. This comes from and 0 less than or equal to Q less than infinity. This comes from the other final one. Okay. So the integrand remains exactly the same, okay, except that the ranges of integration are different. For this process, the range of integration is this, and for this process, the range of integration is this. Okay. So let me just briefly explain where these ranges come from first.
This is gap minus Q minus ME to
Yes, that is gap because it's just as well, because otherwise this would have been imaginary, right, in that range.
By 1 plus Q by T nu.
Yes.
T nu would be replaced by T minus for the last process.
No, it will not.
It will be T.
Yeah, see, E minus temperature is T, because E plus E minus gamma is in equilibrium. It's still in equilibrium, right? That assumption you are making. Otherwise, you have to introduce separate temperature for E plus E minus, right? You have not done that. So Q, okay, let me first explain what Q is. See, remember that minus Q was the energy of neutrino, right? Energy of nu bar. When we have process like this, minus Q is still the energy of nu bar. Okay. So this, if nu bar is in the final state, and nu will be the energy of nu if nu is in the initial state.
you mean E?
Sorry, Q. Okay. So the definition of Q that we have given, right, we have put a minus sign. Okay. That minus sign is valid as long as we are considering final state nu bar. Okay. If it happens to be initial state nu, okay, then we just redefine Q as the energy of the incoming neutrino. Okay, that's the definition of Q. Right? That's how you have to interpret this formula. Okay, where it comes from is that, right? That's the definition. So let's now look at the range. This range, okay, is easy to understand. When you have a process like this, then the only restriction on Q is between 0 and infinity, because that's the energy of the incoming neutrino, and that can be anywhere between 0 and infinity, right? Okay, there is no conservation law that can prevent it, right? Depending on how much energy it has, it will produce appropriate the combination of P and E minus, right? The energies of E minus.
Integrand will remain same.
Yeah, integrand remains the same, right? That's the important point, and that follows from this crossing symmetry, right? It basically is a consequence of the fact that all these processes, right, are related by taking one outgoing particle and moving it to the final state by conjugating it, right? You can see, and so as a Feynman diagram, right, they are the same Feynman diagrams essentially, right? You just have to reinterpret some things as outgoing instead of ingoing. Okay, and that is responsible for why all these integrand remains the same.
When neutrino is in the initial state, what would that mean? That initial state has to be 1 by 1 plus e to the power q.
Yeah, we'll come to that factor in a minute. First, let's try to understand the range, right? So range is okay, right? So Q ranges between 0 and infinity because it's incoming neutrino that you're talking about, so there is a confusion of this energy can be anything. Okay. So let's look at this. Yes.
Why is mass difference is not coming as capital Q in this?
Capital Q is here. Oh, here. Oh, because see, proton mass is less than neutron mass. So any energy that the nu has is constant with energy conservation. You just put the extra energy to E minus, right? Earlier the problem was that the neutron mass was higher than proton mass. So if you have an initial state proton plus E plus, then it better be that E plus has sufficient energy to produce a neutron, right? That constraint is not there here. Is that clear?
In that case, also neutron is the so neutron is
Yes, here also neutron is initial state, right? Oh, they are okay. You are saying because the ME is there. Okay, so let's look at the formula there again. So there it was neutron. Okay, it came from N plus E plus going to P plus nu E bar, right? Okay. So even if E plus has zero energy, right, nu E bar cannot have zero energy because excess energy will be transferred to nu E bar, right? So that's the reason why there is a lower limit on the nu E bar energy, right? If we reverse this process, then it reduces to what I was saying earlier. Right? The neutrino has to have sufficient energy to produce neutron. But here it's just that, I mean, because mass of n is already larger than that of a proton, the final state neutrino will carry a minimum amount of energy.
there won't be any restriction.
Pardon?
In this reaction,
On this side, on E plus, the only restriction is that its energy should be larger than its mass. Right? Yeah. Okay. So for this one, right, we have Mn plus E nu, Mn plus E nu is Mp plus E. So E nu is minus Q, right? Because is it minus Q? No, it's plus Q. Plus Q. So Q is given by Mp plus E plus minus Mn. Something is wrong here. This we already did, no? Or we didn't do? This we already did because that tells us there's no restriction on the neutron energy. It is this one we have to do. Which one? No. This one, sorry, second one. N goes to P plus E minus plus nu E bar, right? So here we get Mn equal to Mp plus square root of P square plus Me square plus nu minus Q in a final state. So Q is Mp plus square root of P square plus Me square minus Mp minus Mn. Okay. So first of all, Q has to be negative because minus Q is the energy, right? It better to be positive, right? Minus Q is energy, so minus Q greater than 0, which means Q must be less than 0. And this one tells us that you see P has to be at least 0, right? So Q has to be larger than Mp plus Me minus Mn. Right? Since P is larger than 0. And this means that Q is larger than, so Mp minus Mn is minus Q, Me minus Q. So that's this. Is this clear? Right? It's just standard energy conservation. If something is confusing, you can just look at it again. Yeah, it will become clear that this is what you have. Is okay? Second reaction, no, it's not going to infinity because Q has to be negative. Because Q is minus Q is the energy of the state, right? So Q has to be negative. Right? That's why the upper bound is 0. Okay, now let's look at these factors. So we started with, which one did we start with? We started with this one, right? No, it's the first one. So this we already understand, right? So let's look at this one. N going to P plus E minus plus nu E bar, right? So what factor do we expect? That the final state nu E bar has to be unoccupied and the final state E minus has to be unoccupied, right? Here, so you expect for this one, we expect 1 minus 1 over e to the power e minus over t minus 1 plus 1 times 1 minus 1 over e to the power e nu over t plus 1 by t nu. Okay. So this is 1 over 1 plus e to the minus e minus by t, 1 over 1 plus e to the power minus e nu by t. E nu by t nu, yes, thank you. Is clear? So now let's convert this in terms of Q. First, let's look at this one. This one gives you 1 over 1 plus. So E nu is Q or minus Q here? Minus Q, right? E to the power Q by T. Q by T nu. This one, energy of electron is the difference between neutron and positron mass, Mn minus Mp, that's Q, minus the energy of the neutrino, plus, which is plus Q. So 1 over 1 plus e to the power minus small q plus capital Q over T. Same formula over there. Right? The interpretations are different, right? Earlier, one factor was coming from the incoming state, the other factor was coming from the outgoing state. Right? Here, both factors are from the outgoing state, right? But it's the same factor. Okay. And I'll leave it as an exercise to check that for this one, also it works out exactly as it is. Here, one factor will be from outgoing state, from incoming state, right? The incoming state has to be occupied, right? The new E. So that's the factor which will multiply the incoming, that P square dP, that formula, and E minus has to be unoccupied. Right? So once you work this out, you will find again that you have exactly the same factor.
We have to add this 6 times.
No, not 6 times. This integral has to be done over this full range. Right? Earlier you had only one range, now you have three ranges. Right? And the other 3 you have to subtract, because that's a reverse rate, right?
It reduces.
It reduces. So this one reduces, the other one increases.
Yeah, this reduces.
Because this depletes the neutron, right? Because it is converting neutrons to protons. The other one will increase the number of neutrons.
How to take this occupation factor in the first example that we did, we said that we have to remove those part of the neutrinos which are already occupied.
Yes.
But there we didn't consider anything about the positrons, like even though they are the mutes.
No, it came. It was there in the formula. The density, the formula for the NDP had that positron factor.
Oh,
Right? So that factor was already there in the distribution formula. Right? So you didn't have to do anything to include it extra.
But that was the number density. How is it coming out to be same as the probability of the state being unoccupied?
Because that factor is that probability, right? Because the phase space integral doesn't know anything about what is the probability of occupation, right? That next factor, right, which multiplies this 4 pi p square dp, is the probability of occupation.
There we wrote, I think, P plus dP.
Yeah, we use the Fermi distribution formula, but in that Fermi distribution formula, the interpretation of the last term is that it is the probability of occupying that state. Right? So that's already included in the Fermi distribution formula. So that's why we didn't say anything about it. Right? We just use the formula.
Somehow seems really surprising that we have considered 3 different processes.
Yeah, but because that's the crossing symmetry, right? The reason that these are equal is because these processes are rejected by crossing symmetry.
But it should hold at this level of calculating rates. Is it, I mean, obvious or like non-trivial?
It is non-trivial, right? But this is what it is, right? Because you see that the way you extract the sigma from the amplitude is via rate. You first calculate the rate using quantum field theory. Then you do all this. So you in the actual calculation of quantum field theory, you calculate the sigma NV, that combination first. If you remember the way we extracted the S matrix element, right? And then you go back and extract sigma. So if the S matrix has that crossing symmetry, right, it's a statement on that rate itself.
What is the exact statement of crossing symmetry of the S matrix?
Well, exact statement one doesn't really know whether it's true or not. Also, people don't know. But for the tree level that you are working, right, is that the amplitudes are related by analytic continuation. Right? You can get the S matrix for incoming state. If you know the S matrix for outgoing state, you get the S matrix for incoming state by simply changing the sign of the energy.
So it's the same Feynman diagram, we just
Exactly. Same Feynman diagram we rotated it, right? In the momentum space, yeah. Well, not even momentum space, it's just you reinterpret that which are outgoing and which are ingoing. The diagram is the same, right? you regard some of them as incoming, some of them as outgoing, right? That's what is changing here. Okay, let me write down the formula for the other rate. At least in tree level, it's certainly true, right? As I said, for the exact S matrix, right, what the precise statement of crossing symmetry is not clear, right? But at the level that you are working, it's certainly true.
But people have seen it at like low level or not.
Yeah, people have. There are some arguments as to what crossing symmetry is, right? But those arguments are not necessary for this analysis. Yeah, I think I have the formula, so now let me write down the other way. R of P to N is total rate per proton. Okay, so a few things change in this formula. This becomes minus, this becomes plus. That's the only thing that changes.
For the last one as well, we'll get the same factor.
For the last one?
0 to infinity. For that process, n plus 2.
This one. Third one, yes.
We'll get the same factors again.
Yeah, same factor, exactly. I didn't do it, but if you do it, you'll find that it's the same factor again.
So the statement diagram holds the case for all these three processes.
Exactly, yeah.
That seemed the factor that the
Yeah, that's not obvious, right? But that is true. Okay, so the change that has happened here, right, is that in the final terms, the signs have changed. Okay. So with this, we can calculate dx and dt, right? So you have dx and dt.
The interval still remains the same.
Interval still remains the same. Yes, exactly. Because it's the opposite process. Eh? Energy conservation is the same, right? You just reinterpret energies differently. If one way can go, the reverse can also go, right? Energy conservation. So dx and dt is minus r n to p times xn plus r p to n times 1 minus xn.
This for one process.
No, total process. This one. Oh, this is, yeah, sorry, thank you, yeah. So I should erase this limit. Yeah. So this is same limit as before. Same range as n to p. Is it clear? So this ratio, sorry, dx and dt now can be calculated, right? I have explicit formula for n to p and p to n. And we know how t nu changes as a function of time. Everything here is known, right? We have already determined how t nu changes as a function of time and how t changes as a function of time. Okay, so you can just substitute here and calculate the fraction of neutrons. The depletion because of the Hubble expansion doesn't really matter because we are calculating ratios, right? Xn is the number of neutrons divided by number of protons. So that overall depletion is not entering this, right? But of course the expansion is entering because the temperatures are changing because of the expansion. So the table that I wrote down last time, right, was basically produced by solving this equation. This is a first order differential equation. You can solve it, right? As T goes to 0, of course, Xn goes to half, right? Because at very high temperature, the ratio should be 1. Right? Starting with the initial condition, you can evolve it and get the answer that we had.
That's the initial condition.
Yeah, that's the initial condition, that the neutron proton ratio was given to be was equal because at high temperature they are equal. No, we use a thermal distribution, right? You remember that it was e to the minus q by t over 1 plus e to the minus q by t, right? And as t goes to infinity, that q by t just goes to 0. So it's 1 over 1 plus 1, right? So that's why it's half. Okay, now we'll use this formula to make a consistency check. And a consistency check is the following. Right? So this is a formula which is valid in general, right? Expanding universe, non-expanding universe is a general formula, right? If you have a gas of protons and neutrons and let it evolve, this is what we get. Now consider a situation, a static situation. In equilibrium. Yes.
Basically, scattering happening in some thermal
Yes.
gas or particles, right? About the expansion is coming through temperature.
How the temperature depends on time, right? So now we are just applying this formula to a completely static situation in equilibrium. Right? So there T nu is equal to T, right? Is time independent. And dx and dt should be 0. Because once you have reached equilibrium, the neutron to proton fraction should remain the same, right? So this tells us that xn over 1 minus xn should be equal to r p to n over r n to p. Okay. But we already have calculated this, so let's try to calculate what this ratio is.
This reaction we need calculate will be in thermal equilibrium and
Nothing to do with?
each other. Chemical equilibrium and thermal equilibrium.
Yes.
Two processes.
Well, it has nothing to do with each other, right? They are independent concepts, but they are still related, right? If there is no thermal equilibrium, right, then the distribution formula you cannot use. Because the formula for xn, we derived a formula for xn last time, remember? Okay. That assume chemical and thermal equilibrium.
So calculation we have done we cannot do, but still it can be in chemical equilibrium even if.
In principle, yes, right? Then you have to use this form, these evolution equations, right? It's only if it's in thermal equilibrium and chemical equilibrium that dx and dt is 0, and you can now try to calculate this.
Neutrino has not decoupled yet.
Yeah, because if it's thermal equilibrium, see now you consider a static situation, right? No expanding universe. So then the neutrino will thermal equilibrate, right? Because it's not competing with any expansion rate or anything.
You mean by not
Yeah, just take the same system, put it in a box, right? Not in an expanding universe. So let's see the ratio, this ratio, right? We have to somehow, you see the only way thing that differs between this and this is the sign of the exponents, right? Okay, so if we can somehow make this into that, then the ratio is easy to calculate, right? So let's see if we can make this into that. So what we have here is 1 over, okay, let's make this into that order. 1 plus e to the power minus q plus q over t times 1 plus e to the q by t. We have set t nu equal to t, right? Okay, otherwise this is not going to work. Okay, we have to set t nu equal to t. So this I can write as 1 over, I just take this common, minus q plus q over t times e to the q over t times 1 plus e to the minus q over t. Okay, that's easy way to change the signs. Okay, but now we combine these two. See, this part we could have done even when t was not equal to t nu, right? But now we see that the e to the q by t cancels e to the minus q by t from here, right? And this becomes then 1 over e to the minus q by t times 1 plus e to the q plus q by t 1 plus e to the minus q by t. So this step, now e to the minus q by t can be taken out of the integral, because it has a constant, it doesn't depend on q. Okay. If t was not equal to t nu, right, then we would have gotten a factor that you couldn't take out of the integral, because you will get e to the minus q over t here and e to the q by t nu over there. Right. So it's important that we had thermal equilibrium, we had t nu equal to t. So now we see that this is given by, so R n to p, right, we saw is e to the q by t times Rp to n, because there is e to the minus q by t in the denominator, right, that's the same as e to the q by t in the numerator. Right. So this was the rate for n to p, right? So R n to p is e to the q by t times Rp to the n. Is that clear? So this gives you e to the minus q by t. Because this cancels and e to the q by t is the denominator. So this tells us that xn, so you can now easily solve it. And this is the same formula I derived last time. That's from thermal equilibrium. Right, so this basically tells us that this detailed balance, right, will work in thermal equilibrium. That if your system is in thermal equilibrium, then it better be that the rate for n goes to p and rate for p goes to n match. Not the rate, but rate times the number, right, matches, so that there is no change in the number of neutrons. Is it clear? Okay. So there is one more thing we can do with this, but that I'll leave to you as an exercise. Okay. And that is to check. So you have calculated this r n goes to p and r p goes to n, right? And you have this integral over different ranges, right, which contribute. You can check that if t is small, right, t and t nu are both small, right? Small means small compared to MEV, for example. Then all the contributions to rp going to n is small. Okay. And for the r n goes to p, right, the only term that remains finite in the, say, small t going to 0 limit is the one where the neutron decays into proton plus electron and antineutrino. Okay. So when t is really low, right, then the contribution comes to this, in this equation, the contribution comes essentially this vanishes and this becomes the neutron lifetime, 1 over tau n, right, where tau n is the E life of the neutron. So this is an exercise. So exercise for t and t nu r t to n is small and r n to p is 1 over tau n. Okay, where tau n, as I said, is the E life of the neutron, and that means that this equation the dxn dt in that limit basically becomes minus 1 over tau n times xn, or xn is some constant mc to the minus t over tau n. But to calculate this constant, you have to do the numerical evolution properly. Right? You could have said that, okay, why not start with xn equal to half at t equal to 0? Right? Because at t equal to 0, you know, half of the things are neutron and half are positron. But the point is that this formula is not valid. This fact that you can ignore this and replace it by 1 over tau n, this is not valid between all the way between t equal to 0 and the late time that you are working. Right? In between, there is a non-trivial evolution that you have to take into account. Right? And if you want an accurate result for xn, you have to do this exercise. You have to basically solve this equation. Okay, so I think I'll stop here. So next time we'll use these results and then start studying the nucleosynthesis process.
So from here we can calculate neutron lifetime.
Yes, I mean, okay, you can calculate neutron lifetime with the same calculation that we normally do in quantum field theory, right? Yeah, you just
So yesterday the calculation, the problem was we proved that if neutrinos decouple, then that will not be there.
yeah, if neutrinos decouple, then it would have gone out of equilibrium, right? But they are not totally gone out of the system because they are hitting the neutron. I mean, for the electrons and protons, etc., there is still a small amount of interaction between neutron and electron, right? Which you have to take into account, right? But eventually, of course, those processes will all go away.
So in practice, if you want to compute all these quantities, you have to do this integral and then plug in the temperature, right?
Exactly.
Plug in the time dependence of the temperature.
Exactly. Right? So given any t and t nu, you can do this integral.
Yeah, but for that computation, the half-life of the neutron, do we need to plug in the time dependence? We don't need to do that.
No, we just take the same thing, this calculation,
Yes.
right? And then use this integral,
Yeah.
right, for the particular range, right? For this range. There is a range of q for neutron decay, right?
I mean, that much is clear.
I mean, at the end, we will get some function of the t and t nu, right?
Yeah, but for small t,
Small
right?
t, so okay.
Yeah, so these functions will basically all become 1, right? Because occupation numbers don't become are not important in that case.
I mean, what is the parameter with respect to, I mean, when is t small, when it's comparable to me? Or
Yeah, t has to be small compared to ME also. ME is half an MeV, right? So t should be much smaller than half an MeV for this formula to hold.
There was a cos theta c factor, I believe. I think the mixing angle.
That is a Cabibbo mixing angle, yeah. But this is a constant, right? Yeah, that's a Cabibbo mixing angle.
That's why we draw a table, right? So we have to get the correct numbers in that table.
Yeah, so that by using this equation.
So there we really have to consider some formation of helium.
No, that comes out later on. Yeah. So far, this table, that table that I gave, assumes only this equation, right? The formation of helium hasn't come in. Right? That we'll do next time, right? Because once helium forms, that table is not valid anymore, right? Because that ignores the process of nucleosynthesis, right? But we need that table because we need the value of xn at the time when nucleosynthesis begins.
Okay. What was the temperature at which this was beginning?
I think it's about 10 to the 9 K, right? About 1/10 of an MeV.
So we have to check whether it is still remain in thermal equilibrium or not with respect to these three reactions.
No, these are not out. These are out of thermal equilibrium anyway, right? Because that's why you have to do all this calculation. If it was in thermal equilibrium, we didn't have to use that equation, right?
Okay.
See, neutrinos have decoupled, right? And weak interaction processes have also gone out of thermal equilibrium.
But we use some of the number density formulas as that in the thermal equilibrium.
For the neutrons.
For when we are calculating this scattering process, sigma in V, where we substitute for n as some.
Oh, yeah, because the E plus E minus gamma is still in thermal equilibrium.
Okay.
Is the protons and neutrons, right? That conversion has gone out of equilibrium.
Okay, yeah.
Right? That's what we are using here. Yeah, so E plus E minus gamma is in thermal equilibrium, and the neutrinos, right, they're not thermal equilibrium, but their distribution is thermal. Right? But because so there are two reasons why protons and neutrons are not in thermal equilibrium. One is that the conversion from protons to neutrons is small, right? And also they are being hit by neutrinos, right, which have a different temperature compared to the photon. That also is the reason why they are not thermal. That's why to get the correct result for this result, you have to also set T equal to T.
That's what you exactly did in the last class.
Yeah, exactly. That's right.
Good question actually. So I was trying to calculate in QED the correction to the potential. So if I remember correctly in class, the way we did was we calculated the one loop diagram, and then we used the 1 pi effective action, and then we obtained some correction like 1 plus, if I remember correctly.
Yeah,
something like this.
Yeah.
And in the static limit, it became this, and we obtained a delta function.
Exactly.
If correct.
Delta of 0.
Yeah, but I was looking at some papers where they are considering scattering processes like this, plus, and there will be these vertex corrections, plus the opposite one. Yeah, they hear those things, and they are saying ki now we'll calculate the T matrix with the, like, let's say for all the channels and all, and then take Fourier transform.
That should also do.
But how will these two be the same? They will not.
Because this propagator ultimately is this is the Coulomb interaction, right?
We are not taking into account this here.
I think this one doesn't contribute to the delta function. These are other effects.
Okay.
Right? But the delta 0 comes only from the this diagram.
Okay. So the contact only comes from the vacuum.
I think yeah, as far as I remember, that's what happens.
But so if you want to calculate the full thing, then